Everyone, let's start our morning session. So the weather is nice. Don't assume that's always like this, though. So our first speaker is Bershtein from CISA, and he'll talk about cluster Hamiltonian reductions.
As everyone, I can start with thanks to organizers, but maybe we are already on the stage. I should also thank participants for coming on the first day, first lecture at 9, and still. Okay, so I'm typed on the board, and this is a report on some projects or some part of. So that means that we will find, in our high paper with 6 authors with this title, it means that you can find with some papers some subset of authors, and then I hope soon we will find another paper with another subset, and hopefully later more papers. So practically today I'm going to report about our work with Mark Prokushkin, but inspiration comes from the whole project. So I have two, maybe adjectives in the title: cluster and Hamiltonian. So let me start with cluster. We already had a couple of talks about clusters in the conference, and I suppose we'll have at least a couple of more today. I'm not going to define what is cluster variety, but I'll rather list the key properties to remember, to have in mind. So cluster. So we have some cluster varieties, and I'll denote usually cluster varieties by letter X, because they're X cluster varieties. And in the very definition, they are given as a union of charts. So union of some charts, let me denote them by U, labeled by something that I denote by S, and S runs through some set, S capital. So, and S is short for seed. So charts are labeled by some combinatorial object that is called seed, and perhaps I sometimes also use this name. And now let us list some properties. So each chart is an algebraic torus. So is isomorphic to C star in some power n, capital, where n is a dimension. These cluster varieties, they are Poisson. The next property is that each chart is not just isomorphic to C star in power n, but also given with a so for each chart good, in some sense, something like Darboux-like coordinates are given. And what else? So this is for any chart. Now, if we move from one chart to another, then there are coordinate transformations for any variety. And in cluster case, they are quite simple. They're given by something multiplied by one binomial, something divided by this binomial, something like this. So simple, rational transformations. And maybe one more property why these varieties are good and interesting, that for this Poisson bracket, there is a natural quantization. Natural and very simple. Usually it's hard problem to quantize, but common story in the cluster world that here quantization is simple. So instead of giving definition, I listed some properties, and now I'll add to this some examples. So what kind of varieties has the structure? From varieties of which kind can we expect the structure? And maybe here, for me, the key adjectives, so this variety should be multiplicative. And so by multiplicative, I mean that the typical example that is not Lie algebra, but rather group. So for example, if you take G to be a simple group, and actually in the very first formula, I implicitly, or maybe explicitly assume that I'm working on the field C, then this group has a cluster structure. To be a bit more precise, the cluster structure is not on the group, but on the open cell inside it. And furthermore, each cell, and by self I mean double bra cell. Each double bra cell of the group has cluster structure. But precise definition, I have not defined what double bra, I'm not recall definition, it's not super important. Another example of the spirit that we can take group, it's simply group, we can add, as I said, told you that for cluster variety we have Poisson structure. What kind of Poisson structure here? Standard Poisson-Lie Skleanin Poisson structure. And for Poisson-Lie group, we have notion of dual Poisson-Lie group. And so dual Poisson-Lie groups, they are also gives an example of cluster varieties. Okay. Let me again label examples by dot. And then one can take some relatives of this example. For example, one can take Grassmannian or flag varieties, and also similar to here, practically we will have some cells in such varieties. As I told you, there is natural quantization, and what can we obtain as a quantization? Since I told you that we have Skleanin Poisson bracket or matrix Poisson bracket. So after quantization, we obtain something like quantum groups. And so we can obtain quantized universal enveloping of Lie algebra, or we can obtain quantized algebra function, or we can obtain some other example spherical Daha, and something like this. So something that in terms of integrable system would correspond to trigonometric integrable system, relativistic integrable systems, algebras like this. Okay, and the last example, and actually it will be an example that I use mainly in my talk, it is a moduli space of, again, I need some adjective framed, local systems on surface. Or yes, real surface, complex curve. So pictorially, we pick something. So let's take P1 with some set of punctures. I don't know, it's 4. And the local system, which is a representation of the fundamental group, is determined by the following data. We pick some base point, pick some curves that form a basis in the fundamental. This is corresponding cycle, corresponding path form a basis, gives the generators of the fundamental group. So, gamma 1, gamma 2, in this case gamma 4. Okay, let me write gamma k. And for each of these paths, we construct the monodromies. It is some matrix, so it is a set of matrices, M1, Mk. In this case, they belong to some group G of the same time as before, complex simple group. The fact that I pick all encircle all punctures in this case leads to the fact that product of this matrix is equal to 1, and everything is defined up to a joint action of the group itself. So I gave you genus 0 example, but for other genuses also work if you have at least one puncture. And again, this is like multiplicative type example. So data is in terms of the Lie group. So one can use it as a generalization of either these or these examples.
So the adjective framed is manifest where?
Yes, so the word framed, and this will be actually, it will have some importance for the talk. So the word framed means that, that some additional data. Okay, I'll try to use chalk, but if please comment if it will be visible. So it means that we pick some additional data that is invariant flux in points. By points, I mean punctures, or sometimes we have marked points on the boundary, something like that. And invariance with respect to local system. Typically, this data is typical, at least in the example that I drawn, this data gives it just some finite cover of the standard modular space of local system, and cluster structure exists on the cover. Okay. So this is a type of variety that I'm going to think about, or type of algebra that I'm going to think about after quantization. And the question for this project or whatever, how reduction talks to cluster structure. By reduction, I mean you can pick any reduction you like. So in the title I used word Hamiltonian, and we know that a lot of important Poisson varieties appears as a Hamiltonian reduction of something simple in integrable system, and in representation theory a lot of interesting algebras, like typical, like something like double algebra, appears as via Hamiltonian reduction. In this, so in principle, I can stay with the word Hamiltonian, but in this case, we not always have this, like it's honest Hamiltonian action, Hamiltonian reduction with respect to some group action. So this it can be what's called Poisson reduction, or what's called coisotropic, and probably one can find other examples. So there are some versions of the definition of the reduction that I'm not going to define at this second. So so we can, so there are a class of varieties where we have cluster structure or expect cluster structure, and this class of, on the other hand, many important examples obtained via Hamiltonian reduction. So can we, for example, if we know cluster structure on the original variety, can we expect that we will have cluster structure on the reduction? Or even if we can expect, can we construct it in terms of the reduction, the structure original? Cluster structure on M here. So M depends on the curve, on the surface on G. It is, yeah. So I will again cite it in the, so this is, it is defined by 4 Goncharov-Kenyon, and for the purposes of the 45-minute talk, I'm going to use this as a box, black box. So there is cluster structure, but maybe during half-hour coffee break I can define it. So here I pose the question in quite general world. So assuming that we saw somewhere reduction, somewhere cluster structure, but of course in mind we have some list of concrete examples, and generally, quite often this example corresponds to the fact that something not in generic position. Even here, when I talked about simple groups, so further says that we have structure cluster reduction on the group, and then I become more honest, saying that actually it is, so we have like on the open subset, but also we have on the other set where something not in general position. So this is reduction issues also about something not in general position, not in generic position. Okay, to be more concrete, so today, so we will talk about this example. So again, the same adjectives: framed, local systems. So system depends on the surface, and by letter S I actually encode a lot of data, not just surface, but punctures in it, and if you have some boundary components, marked points on the boundary, everything like this. So and in the example, I will take punctured disk with 2 marked points on boundary. And the picture is what? The disk. It's topological, so it's not a circle, it's not a problem, so it is punctured. We have puncture here, and we have 2 marked points on the boundary. Of course, this is, I mean, at least for me, it was not the first surface that I thought about. Why do we consider it? So first, not the main, but just to have some idea in mind. So if we, so this here I'm talking about local system topological data. But if we somehow find pick some complex structure and apply something like Riemann-Hilbert correspondence, so we have Riemann-Hilbert. This corresponds to linear differential equations on a linear differential equations on a sphere. And the fact that we have one puncture here, it means that we have one regular, and boundary condition means that we have one irregular singularity. And this is actually very concrete regular singularity. There's two appears in the description, but I mean, we can't have one regular and one irregular singularity. What do I mean by local system on this here? How to describe it more explicitly? So the fact that we have invariant flags on the boundary with some additional pinnings and so on allows us to have some given basis on the both segments on the boundary. And using this basis and local system, we can compute parallel transport. We can take the basis on this boundary, transport it to another boundary, and compare to the basis given that we have here. And actually, since we have puncture, we have two ways to compute it. So we have two passes, one above the puncture and another below the puncture. And if we compute the parallel transport, we obtain two matrices. And I denote them by L plus and L minus. Why I have denoted like this? Because due to this framed structure, the fact that we have fixed flags or barrel subgroups here and here, one can, I mean, it follows immediately from the definition that both of these matrices are triangular. So L plus is a upper triangular matrix. Maybe already, in order to draw all these formulas, I will write that from now on my group is PGLM. So L plus is upper triangular, and L minus will be lower triangular. And Poisson bracket on them is a Poisson bracket on the dual Poissonly group. Or if you prefer, after quantization, we will have quantum universal enveloping algebra. So this is a surface that corresponds to the quantum group. So, our matrix Poisson bracket like an equal 6 to 3 equal to 3. 3 terms equal to 3 terms. RLL is equal to LLR. Like, I mean, classical limit of, I mean, I gave you, said you quantum relation, but so I took RTT realization of quantum group and then classical limit. So the Poisson bracket between this parallel transport matrices can be computed, for example, using formulas from paper by Chekhov and Shapiro. That I think we will hear in 2 hours. Other questions?
Which data is associated with process and two matrices, where it's flat, where it's vectors, who's preserved?
So we have a puncture disk, and then for any closed curve, we can compute monodromy of the local system. And if our curve goes from the boundary to another point of boundary, we can compute parallel transport. And here I'm computing parallel transport. I took two arcs and compute how the basis on each edge connected after parallel transport is connected to the basis on this edge. What about what? Yes, so this crosses decomposes boundary circle into two segments. And on each of the segments, therefore, I have given basis. So for each of these crosses, I have given flag. And then if I have two flags, I can construct bases. Here are some details that I'm meeting. So if I have two flags, I can construct projective bases. I can construct a set of one-dimensional subspaces. But using some additional data, I can pick a basis. And using this, I have basis here and basis here.
When you
This flag. It is a matter of convention, but L plus preserves this flag and L minus preserves this flag. Here we have puncture. And we can, in addition to the arcs that I drawn, we can also draw, if, I don't know. Is there any experience about red or blue color? Are they visible? So, I already picked red. Okay, so we can draw also curve that encircle the puncture and compute monodromy around on this circle. And there are actually different ways to do this. One way we can do it, we can compute it somehow near this puncture, and therefore this monodromy will preserve the flag here. So this matrix M is by definition will be also upper triangular in some basis. In some basis somehow relate to this puncture. But
so it's not equal to L plus L minus inverse.
No, not equal. Maybe I delete this formula to avoid confusion. What I want to say is that we can compute monodromy around this puncture using up to conjugation, using L plus and L minus, because this local system, we can take any curve in this class in the fundamental group. For example, we can take this big curves, so monodromy is proportional to L minus inverse L plus. That is a standard map from the dual Poisson-Lie group to the original Poisson-Lie group. That was, I mean, already used in this conference, and everybody knows. As I already answered to, I think, Dima's question, so there is a cluster structure in this module space of local system, and now it's time to decide names. There are several papers by subsets of this list answers that construct a cluster structure for any S, in particular for this S, but this is for the case of generic monodromies. Generic local systems. And today I'm going to talk about case where something not in generic position, and by I'm talking for 20 minutes already, so it's time to move closer to the subject. So today, the condition on the local system will be as following. So this local M will be conjugated to the diagonal matrix. So some generic assumptions still exist. So I assume that the matrix is semi-simple. But I no longer assume that it belongs to the subset of regular semi-simple elements. So now I assume that this diagonal matrix is of the form M1 mu1, M2 identity mu2, and so on, some mk I mu k, where this mu1, mu2, mu k form, so mu, as it is mu1, mu k, is a partition of N. So the monodromy is assumed to be conjugated to the matrix of the form M1, M1, M2, M2. And this I stands for identity matrix. Maybe it's not the best notation, but I hope it's okay. And maybe I mean, we are not the first who thinks about this special monodromies, and they appear in the physical literature. That's maybe mentioned later, but here without appropriate discussion, just list name of people. But I assume that we are saying something new. So I hope I at least partially motivated our choice of the surface, because, I mean, due to this relation to the quantum group. And maybe more geometric way to motivate it is to say that here we are solving some sort of local problem. So we took some regular singularity and assumed some special behavior labeled by partition in this regular singularity. So I'm not saying that always, but okay, let me write in a humble way. Sometimes, if we have some global curve with many singularities, we can somehow decompose it into this punctured disks, and therefore reduce problem for the cluster construction for this global curve, to the problems to the local problem. So this is. So I'm not so on this problem. We actually solve more than just one surface. There are a list of examples for which this is sufficient. Times global glue it from local. Okay, so we are solving this problem, and so I'm going to say to construct cluster structure on the model space of local systems on the punctured disk with this conditions that we have special monodromy around the origin. In order to, as a particular case, it includes, of course, the for Goncharov-Kenyon story, that in which case this partition is all these m's are equal to 1. This partition, just all eigenvalues are distinct. So I need to recall something about the original construction. This, I'm not sure it was clear from my exposition, but this cluster story quite often rely on some combinatorics. So this good Darboux-like coordinates, they are, in terms of Poisson bracket, they are the Poisson bracket, they are logarithmically constant. So Poisson bracket between these good coordinates that I still have on the board has a formula xi xj is epsilon j xi xj, and log constant. And this, moreover, this epsilon j, this numbers epsilon j, they're integer. And therefore, then can be interpreted combinatorially as the adjacency matrix of some oriented graph. So we can think about epsilon j as a number of arrows from vertex I to the vertex j minus number of arrows from vertex j to the vertex I. Therefore, instead of writing the matrix epsilon j, I can draw a quiver. And this is, of course, how I will think. So the quiver, again, will correspond to this surface, which let us punching disk with 2 marked points. And here how it looks like for the group PGL4. I'll need some space for this. I'll draw it some detail, but of course I'm not. I will refer to it too much. So x1, x2. Now we have here y1, y2, y3, y4. Now z1, z2, z3, z4, z5, z6. And here we have also some v1, v2, v3, v4, v5, v6. Okay, so here are the vertices. Overall, should be something like 18 vertices. Since this is related to the group, the number of vertices is more or less in squared up to some Cartan part. So 18 is more or less the same as 16 that is 4 squared. And okay, I will not bother you with orientation of arrows. So I just draw lines. Yeah. Z6, this one. This is close to true, honest pictures. Now we want to assume that we have special monodromy. So my geometrically, I don't know, it's geometrical. It means that we have subvariety in our cluster variety, or the not in cluster variety, in the modular space of local system. That is can be defined in this coordinates via some ideal. So the ideal defined by equations that monodromy is proportional to this special matrix, 1, I1, mk, ik. And how this ideal looks like, let me give a couple of examples. So I first draw partition, which is mu, and then ideal. So it will be partition of 4. This is PGL4 local system. So if this partition is, if this partition is 1, 1, 1, then there is no ideal, no special condition. If this partition is of this form, then ideal is generated by 1 plus x1 equal 1 plus x2, in terms of equation equal to 0. If partition is of the form 3, 1, then we will have more equations. 0, 1 plus x1 is equal to 1 plus x2 is equal to 1 plus y1 equal to 1 plus y3, 1 minus y2, y4. Variable x is the variable that corresponds to this vertex of the quiver. In terms of the local system, so this is the closest variable to the puncture that is here. So it's correspond to, in terms of x, you can describe local system on the invariant two-dimensional subspace of your of the fiber of this puncture. So we have give a fixed flag in the puncture, and the closer vertices to the punctures and smaller subspace it corresponds to. But I mean, in general, also Fogg and Goncharov gave some formula for all these matrices in terms of these variables x, y, z, v, and.
Is it related to Fogg-Goncharov-Kenyon quivers?
It is their quiver, yes.
Exactly,
it is exactly. I mean, up to frozen part. Yes.
There's an x, y, x to y, y, y to y, z to y 2 times y.
These are equations that, so the monodromy condition reduces to this equation. This is a result of computation. So this is, I already defined the ideal in terms of partition, and then in some chart. And now, if we take one more partition, then we still have the same condition that correspond to these two, but now we'll have two more conditions that could look a bit cumbersome. This is one, and another is something like this. The minus of the product of the upper triangular matrix conjugated to the product of L plus of N or minus. This is not literally plus. This is rather matrix M. And with this ideal, we have at least two problems. First, then, if the partition grows, then the ideal becomes more cumbersome. Second of all, this ideal is not Poisson ideal. The subvariety given by this ideal is not Poisson, so it can't be cluster subvariety. And in order to have something Poisson, we need to do some reduction. And in this case, reduction will be coisotropic. But I think in Romanian, in the last 5 minutes, it's much, instead of talking about coisotropic, I would prefer to state theorem. And I mean, I said this is one theorem, but it will have 4 items, so one can view it as a 4th theorem, so whatever. So A, that exists of set of, I would use the word admissible charts as admissible, such that for any seed in this admissible subset, the subvariety, our special subvariety, so the ideal G inside of algebra functions this for S, is determined by the binomials of the form 1 plus monomial, where I runs from 1 to some number. And this Mi is monomial. So in some special cases, hook partitions, the original chart works. But for this rectangular partition, you see this is not monomial. It's not a binomial. B. So just a map from the subset given by this ideal inside US to the another cluster chart UT. And the coordinates here, the W, is given again by some monomials in terms of the coordinates in this chart S. And moreover, this UT is a Hamiltonian reduction of the chart above via this ideal. No. No. Okay. C that exists a Poisson map from the algebra function, the product of two barrel subgroup to the function on this reduced variety. So this reduced variety is a union of these charts that denote by T. And our local system now becomes described in terms of the coordinates of this reduction. And D, and good news is the last, that any two charts, UT and UT prime, are related by mutations in this new coordinates W. A plus. And the proof requires some combinatorics, usual standard two cluster algebra story. In some places, it's good to use our matrix commutation relations or Poisson brackets if we work classically. And even more interesting, in some points we need some modern technique, this algebraic weaves developed by Casal, Gorsky, Shapiro, Semenyakin, based on the works of Elias. So it really requires some algebraic techniques inside. But instead of finishing with the details about proof, let me just say a couple of words to put, again, this problem somewhere in the whole picture of, I don't know, subject of the conference, if you want. So here I gave you a classical result, but after quantization, these maps will give you maps from UQ of G to something. So in the sense, it gives you some representation of the quantum group. And this is some sort of parabolic representations. So representations that have constructed in the original to like principal series. And this is, here you already see some parabolic structure in the very definition. And another example that in terms of integrable systems, if we take maybe not this surface, but rather one function torus and impose some special conditions the function, we will define Ruijsenaars models, trigonometric Ruijsenaars model. So in order to have cluster structures in the Ruijsenaars model, we need to use this or some other reduction procedure. The original for Goncharov-Kenyon does not give acceptance to case. And honestly, our main motivation to study this cluster structures is Guyota conjecture. Guyota conjecture that states that a Coulomb branch for any four-dimensional supersymmetric theory should have cluster structure. And this series gives us some bunch of examples that some reason to where to expect these cluster structures and to construct. So maybe I should write this keywords for D and Coulomb. And in the sense that, so first, first motivation was for representation theory. This would be for integrable system, and maybe I can call this related topic.
Thank you very much. Let's thank Misha. Questions?
Misha, is it reasonable and feasible for symplectic group, for the symplectic group?
I mean, for further types, so I could concentrate on types A, but definitely the problem is reasonable for any type, but I don't.
Are there some interesting examples?
For sure.
So my proper interest is the relation with the electrical networks, but maybe there are some different.
I think there are, but I'm not.
Okay.
I'm already have sufficiently many problems in type A.
Misha, do you have a cluster structure for this reduced case?
This is a theorem, yes.
Huh?
This is theorem, yes.
Mm-hmm. So just this one. So
for one puncture and a non-puncturing disk.
in this case?
In this case, yes.
Okay.
Already have the content.
So I stated classical theorem. So this parabolic representations, their cluster interpretation, they're given in the paper of Ivan Ip. You know, and we can prove that the cluster structure obtained like here coincides with the one that he somehow guessed.
Yeah, very interesting topics. My question regarding the finite integrable systems. You give some examples in the end.
Yes.
Do you have other examples like totalities is included in your examples or others?
So examples that we have here, they are so in the classical language, the phase space will be finite dimensional one. So here I give example of Ruijsenaars, and since I already started to give names, the cluster structure of Ruijsenaars is Diffrancesco, Tidem, Shapiro, Schrader. Another example would be some XXZ spin chains, open or closed ones. They also fit into this example. But this is the spirit of the example. Yes. Actually, Toda system, but again, finite dimensional, not finite dimensional Toda systems. They also have cluster. Relativistic Toda, they also appear cluster. Periodic or not periodic open also can original Toda system, but finite.
So I think these guys have some kind of way to get from Ruijsenaars to Toda, right? So by some cluster.
Yes. So Ruijsenaars correspond to torus. If you degenerate it somehow, you'll become. The Toda correspond to surface with some irregular singularities.
More questions?
Yeah, thank you very much. Can you explain a little bit about this for the equals to Coulomb branch with this moduli space of local systems? What's the relation between these two?
I mean, you asked. If you seriously ask, explain that the honest answer is not. But just to have a few words and just to say a bit more words. So there is a class of four-dimensional series, so-called class S series, that are constructed from the complex curve. And this moduli space local systems, they correspond to Coulomb branches for this class S series. But there are other classes, gauge series, for them, they also expect cluster structure. There is intersection between gauge series and the class S series. So. But if you want to put this somewhere in the some picture, then this corresponds to class S series. That's probably heard.
More questions? Questions from Zoom? No. Okay, so before we get caffeine.